Okay, so you'll tell me when to start?
Yeah, we have started. So now we have on our hackathon a talk by Christopher Manning, who is professor of linguistics and computer science Stanford University and leading scientist in the field of natural language processing. So, okay, we are ready to hear you talk.
Thank you very much, and apologies again for the late beginning of this, and I know I'm keeping you late at night, but maybe if you're an all-day hackathon, that's okay. So what I wanted to do today was tell you something about my own work, which is centered around an idea of trying to make some use, but not too much use, of compositional linguistic representations. So let me say just a little bit what I mean by that. So in the use of human language in computer science, there's a spectrum between a widespread use of extremely simple models, in particular the bag of words model. So actually at Carnegie Mellon University, they have this wonderful art installation that you can see a picture of there on the left of. They have the bag of words, which is a lovely thing. But it's very commonly we just sort of say what words are in a document and just use that. At the other end of the spectrum, if you go and look in linguistics, that it's commonplace in linguistics that people are using incredibly complex and nuanced representations of linguistic structure, which by and large, most computational people feel aren't useful and haven't attempted to implement. But what I'd like to hope and want to argue for today is that there's space in between those things for some basic linguistic structure that's helpful for natural language applications. And so if I take one more moment of inspiration from linguistics in the recent work of Noam Chomsky and colleagues, that they've wanted to argue that a central factor of human language is that it has the property of recursion, and that's basically it. So if I generalize just a little bit from there, the theme that I'm going to concentrate on today is the idea that if you want to understand complex things like language, you have to be able to understand the parts that they're made up of and how those parts then combine to give the more complex wholes, such as this diagram here of a Ducati engine. And so my basic argument is that artificial intelligence requires being able to understand bigger things from knowing about smaller parts, doing composition. Of course, that's not the only thing it requires. It also requires other things like planning and knowledge, but this is a big part of what we need to have. And so that's something that I've concentrated on in my own work in deep learning. I know in this hackathon you're hearing a bunch of talks from different people on deep learning, but a particular interest of mine has been how can we not just have word vectors and word representations, but how can we get beyond that to know when larger linguistic units are similar in meaning? So we'd like to know that a snowboarder leaping over a mogul is similar in meaning to a person on a snowboard jumps into the air. And how do people do this? Well, they interpret the meaning of larger text units by doing semantic composition of smaller elements. We start off knowing what words mean, and then we can put them together into phrases, including for phrases that we've never heard before. And so there's been a lot of work on representing the meaning of words as vectors in a vector space, and that's been an incredibly successful approach to lexical semantics. And I was interested in the idea of, well, how do we get beyond that and have representations for the meaning of longer phrases? And the hope has been maybe what we could do is find a way to take these longer phrases and also give them a meaning inside the vector space. And the question is then how we might go about doing that. And so the idea that we developed was what we will actually do is semantic composition in a fairly linguistically motivated fashion using the principle of compositionality. So we'll determine the meaning of a phrase or a sentence by taking the meanings of the components that make it up and then have a composition function that can combine them together, and then we'll get the meaning of a phrase or a sentence. And this I've mainly motivate and will mainly motivate from the point of view of language, but it's important to realize that this idea of composition applies in many other places as well. So when you understand a complex mathematical formula, well, you'll tend to do that compositionally. You recognize the front part's a normalizing term and the right-hand part also has some more structure to it. And when we look at visual scenes, well, visual scenes are also composed between smaller pieces that go together to make up the whole representation. And so the question is, can we then build these kind of meaning composition functions in deep learning systems? And what I'm going to do today is, in the first part of this talk, tell you some of the work that we've done on deep learning meaning composition systems. And then the second part, I'm actually going to show you some non-deep learning work exploiting some other ideas from natural logic, which have also been centered on this idea of how to do composition in natural language. Okay, so for the deep learning part, we built a sequence of models that are in the space of tree recursive neural networks. So when we want to build up the meaning of a phrase, what we're doing is taking the meaning of its components, putting it through a neural network, and then we're getting out of that representation of the meaning of the phrase, and perhaps sometimes a score of its goodness as well. So more concretely, what we're doing is we have vectors for the words, we're putting them through a neural network, which in the simplest case, version 1 here, we're just concatenating the two vectors, doing a matrix multiply, adding a bias term, and then putting that through a tanh nonlinearity, and that's then giving us a representation of the phrase. This was the very first model that Richard Socher and I came up with back in 2011, and it started us off in this direction. In retrospect, it wasn't a very good model. There was only a single weight matrix in the whole system for the composition of everything. And if you think about this model a bit more, since we just concatenate the two words here, you can think of the two parts operating separately. So there's kind of like there's a W1 and a W2 that multiplies each part. So the two words and their meanings don't really interact together properly. And so I'd argue that this pretty clearly isn't adequate for a human language composition function. But it was already enough to get us some nice results, and then it was a starting point for more complex models. And I want to go on and sort of give you a quick survey of some of the other models we went through and then concentrate a bit more on the more recent ones. So moving on from there, we had the idea that, well, a simple way to get a bit more power would have to be to have the composition function depend on what kinds of things are being composed. So a verb taking an object would compose differently from an adjective modifying a noun. And we thought that that could be a neat idea for building a parser that was better. So there's been considerable success with using straight symbolic context-free grammars for basic syntactic structure when used in a probabilistic context-free grammar context. But it seems like those models can model the syntax of a language pretty well, but not really the semantics and the meaning as to what should modify what. And so the hope was that what we could do is we could take phrases of a particular type, B and C, which have a vector representation, and so then when we combine them together, we're still using the same kind of simple neural network to do the composition. And the difference, though, is that the weight matrix is specific to the kind of categories that we're joining together. And this actually worked quite well to improve the performance of the Stanford parser in our continuous vector grammar parser. And a nice thing about it was that the semantic models could actually learn something about where meaning is conveyed in words. And so one way you could see this is it learns what are the heads of different constituents. So if it's joining a noun phrase and a conjunction, it knows that the noun phrase carries most of the semantics of that. Whereas if you're joining a possessive pronoun like her or its with a noun, it realizes that most of the meaning can be found on the noun side, and that's stuff that can be learned automatically. But still, we wanted to get further than that and have the idea that the meanings of words really interacted with each other when you did linguistic composition. And so trying to think about how to realize that, our next idea was to turn to matrices. So what we want to model is if you have something like very and good, that its meaning just can't be it's very and it's good. Rather, very modifies the meaning of good, and so it produces a stronger version of good. Whereas if you had something like not good, not modifies the meaning of good and takes you to the other end of the spectrum. And in conventional semantics, you do that in lambda calculus by making very a function that takes good as an argument and modifies its meaning. And if you think about that in vector space terms, it seems like the natural way to do that would be to have a matrix that can then modify the meaning of a vector. Because in general, it wasn't clear which functor and which side was going to be the argument, what we did is said that each word is going to be represented by both a vector and a matrix. And then when we combine the meanings of words, we're going to create a new vector for the phrase, which is done by multiplying the alternating matrix and vector parts, multiplying that by a weight matrix, and then putting it through a nonlinearity again to get an output representation. And then also we would build a new matrix for the phrase, and that would be formed from the matrices of the kids multiplied by another weight matrix. So again, this was a model in which we could actually get some neat results. So one neat result was we could use this as a model of relation extraction. So we wanted to learn particular relationships, so that in my apartment has a pretty large kitchen, that kitchen is a room, a component inside the apartment, and similar relations of the kind that people extract relations of something being located at a place and being spouse of and things like that. And so we were doing that for putative entities connected by a relation, we're computing a representation of the node that joined them and then putting that through a softmax classifier to decide what relation held between them. And this we were able to do really rather successfully. So these charts compare previous results on this system, on this task, which was a SemEval task from 2010. And what we found was that our previous basic tree recursive neural network sort of worked okay. I mean, you know, much better than the simple SVM, not as well as the very feature-rich models that people had explored before. But the matrix vector RNN worked much better. And then by starting to not just use word representations, but a few features of our own, we could sort of push up the numbers to beat the best previous system, but using a lot less hand-coded features than in the system that's represented here. So that was nice. On the other hand, this matrix vector RNN model was in many ways very problematic when you looked at it more closely. And a lot of the problem was with these matrices. So firstly, matrices just involve a lot of parameters which are hard to estimate well. We dealt with that to some extent by just shrinking the size of our vectors, so that if we shrank the vectors to length 25, the matrices were only 625 elements. But that was bad in another way, since it's generally known now that bigger word vectors normally work better for tasks. And we didn't really have any good way to pre-train the matrices for words, so we just randomly initialized them. and our ability to compose their meanings was fairly weak. So if you looked at the matrix representations that they were able to learn, they weren't actually very successful at representing a good matrix that could multiply to modify the meaning of another word. And so what we were then looking for was, could we come up with a different way where word meanings could closely interact without requiring the huge number of parameters of the matrix vector model? And so that led us to develop the tree recursive neural tensor network. And so the idea of that is that, well, a very simple way to have two words meanings interact would be to say, well, let's just take their dot product. That's an interaction that's sensitive to word meanings, but that only produces a single number back. And so if we wanted to do more than that, we want to get out a vector of numbers. And well, a way we could do that is we could generalize the dot product a little by sticking a matrix in the middle. So that would still produce a single number back, but it could be mediated by the matrix to be a more general composition operation. But if we then replicated that unit the number of times as the length of the vector, which is equivalent to putting a three-dimensional tensor between the two vector representations, then the result of this vector, three-dimensional tensor vector multiplication would be to produce another vector of the same size as our word representations. And so that was the idea of our neural tensor layer. We combined it with our previous layer, so we had both a multiplicative relationship and the old concatenative relationship. I'm not actually sure if this part on the right is very necessary, but we can made in the models we built. Okay, and a place in which we showed the utility of these models is whether a piece of text is negative, positive, or neutral. So if you, in many cases, sentiment is quite easy. So for long documents, you can sort of just count up the positive words and negative words and have some simple bag of words classifier. So for long documents, you can commonly get 90% sentiment from bag of words methods. But for short pieces of text, it's harder. And so if you look at something like sentences from Rotten Tomatoes movie reviews, you get sentences like, with this cast and this subject matter, the movie should have been funnier and more entertaining. Well, this has positive words like funnier and entertaining, but you're meant to decide that this is a negative statement. And so how might you be able to do that? So we thought that one of the problems was that there just wasn't actually adequate data to be working these kind of things out. And so, oops, that didn't work. So one thing we did was construct a sentiment tree bank where we actually took phrases and of sentences and asked Turkers to judge them for sentiment. And so we actually have for whole sentences their different parts of their structure and whether it's positive or negative. And that actually gave us a richer source of supervised training data for training models. And it allows us to train and test for what meaning compositions look like. So having this richer source of data actually helps all models, that even if you're just building a naive Bayes bag of words model, its performance goes up significantly when trained on this data because you can separately train it on each phrase that has a sentiment rating. So the naive Bayes model is much better able to work out what are positive words and what are negative words. Somewhat worryingly, our existing neural network models, when trained on this sentiment tree bank, actually work no better than a naive Bayes model trained on it, which showed us we had some work to do. But fortunately, we had this new idea of the recursive neural tensor network, and it provided a more powerful model. So by using it with both its multiplicative and additive representations, we were able to train this model over the tree structure, training all the weights jointly with gradient descent. And this model then worked considerably better. So we've now got a model that's working at least sort of 3% better than these other models. And we could look at it and we could see it doing interesting things. So here's an example of it working on the sentence. There are slow and repetitive parts, but it has just enough spice to keep it interesting. And you can see the model is able to detect that this first part of the sentence is negative, the second part of the sentence is positive, and when the two parts go together, the whole sentence ends up positive. And it works much better on these kind of sentences than any of the preceding models, which really can't tell apart successfully the different parts of sentences and how they combine. Another good illustration is from looking at negating of negatives. So you can strengthen negatives incredibly dull. What happens when you negate negatives not dull is that a negated negative becomes a mild positive. It doesn't really become good, but it becomes sort of okay. And if we look at the different models that have pre-existed, when you had a negated negative, all of the preceding models basically said negating a negative didn't change its rating at all, which partly reflects the fact that negation by itself is kind of negative. If you don't use negatives if you want to sound a positive person. But the RNTN is able to capture that negating a negative makes things more positive, if not very positive. So that was great, and we were very happy with that. Our happiness dissipated a little over the next year because a couple of people at Google, Kwokler and Tomasz Mikolov, now at Facebook, then developed this model called the paragraph vector model. And the paragraph vector model is sort of a glorified word-to-vec model where it has an extra representation it learns to represent each paragraph, but it doesn't make any use of syntactic structure. And they showed that they could get their paragraph vector model to actually work considerably better than our recursive neural tensor network model. So that sent us back to the drawing board. But last year, we came up with an even better form of tree composition model, which picks up the idea of using long short-term memories. So in sequence models, people have had enormous success in deep learning by using long short-term memory sequence models. And so it occurred to us, well, maybe we could take that same neural composition unit and then apply it to tree structures, and maybe that would allow us to do even more accurate tree composition. And so Kai-Sheng Tai started working on that idea. So the idea of LSTMs is that when you are stepping through a sequence, you have these extra gates which are themselves worked out by neural networks, but have a probability come out of them which says how much to use different things, how much to pay attention to the input, how much to use the internal state in deciding the output, how much to remember from one time step to the next. And particularly these forget gates tend to be very central to the operation of LSTMs. So we wanted to use those and then combine it with the structure of sentences to keep the same ideas of tree-structured composition. And so that gave us the tree-structured long short-term memory networks. And so what we're doing is when we have a constituent like the tall tree, it has a head word tree and then some children that are dependents, that and tall. And so these would go in as multiple path states which would have forget gates each attached to them, and the head word, the tree, would be the input, and it would create the next unit in the LSTM, which would then continue to climb upwards. And in this way, we could generalize an LSTM to any branching factor, so that we've got the head word of a phrase being the input, and each of the other dependents would then be going in as if it was from the past via a forget gate. And our LSTM model can selectively decide which parts of which of the different children it then pays attention to in doing composition. So nicely, this actually worked, and it worked not only considerably better than our previous model, it worked at least a little bit better than paragraph to vector, and it also, interestingly, a lot of recent work in deep learning has just used sequence models for language, and they've actually been quite successful. But I think one of the nice results of this work is we have a good comparison between just using a sequence LSTM and a tree LSTM, and we actually are getting significantly greater value from using the tree LSTM structure. So this is just doing two-class sentiment, positive versus negative. We also have results from doing finer-grained sentiment where you're precisely trying to work out how positive or how negative different statements are. And in this configuration, we're actually getting bigger gains from the tree LSTM structure. So that actually seems a pretty good model, which we've then started to use also in other contexts. As well as using it for sentiment, you can also use it for other tasks. So this is working out semantic relatedness using the 2014 SemEval task SIC. And again, the tree LSTM works better than a simple LSTM and better than the various other methods that were entered into that SemEval task. And so here's just one visualization of a tree LSTM at work where the whiteness of these forgets and then saying how much attention is paid to different nodes. And you can see it's correctly deciding that you want to remember about waste and you want to remember about good, but when these two combine together, it's waste that dominates, so this gets a negative rating. Okay, so that's me talking about neural network composition. I now wanted to say a little bit about some different but related ideas of how we could use natural logic models for doing reasoning about language and doing question answering. So natural logic is an idea that's existed variously for a long time of can we do logic directly over the forms of natural language? So it's kind of a weak proof theory over surface linguistic forms. So if you look at natural logic, this is really where logic started with Aristotle. So if you've seen Aristotle's syllogisms like Socrates is a man, all men are mortal, therefore Socrates is mortal, that's doing inferences directly over human language. So that's a form of natural logic. The idea was revived by George Lakoff in the 60s, and then it was further picked up and developed by Johan van Bentham in the Netherlands. And so he developed a formalized weak proof theory over surface linguistic forms, but it seemed to us there was nevertheless one that can model many of the common sense inferences that we wish to make. So my former student Bill McCartney first worked on this and developed an extended calculus of natural logic. And so that model was then picked up by a student of Johan's, Thomas Hicard, who formalized a lot of that model. And now we've sort of been looking at how can we use this model for large-scale inference. So what we'd like to do is learn how to reason about the truth of hypotheses based on the facts that we can learn around the world from a lot of text. So for example, we might want to learn what country Obama was born in, or what do cats play with, or where is baseball played. So we're assuming that we have as a resource a large knowledge base. And in many contexts, people assume that that large knowledge base is a structured, formalized, logical knowledge base. But in our case, we're just going to assume the knowledge base is pieces of text that we found around the world. So we read sentences somewhere of a cat ate a mouse and that all cats have tails and all kittens are cute. And we'll just have a big pile of text. In particular, there's no normalization of that text, no claim it's all consistent. And so the hope, nevertheless, is that we can do a middle level of composition and inference to be able to better understand text and to work out the answers to questions. So if you use very shallow IR bag of words models, they're easily thrown off if you just match words and don't understand the sentence context. people have tried to use deep logical reasoning for text understanding, which in theory is very precise, but in practice, the ability to make the inferences you want is normally not there, and you don't have the structured knowledge that you'd like to have. And what we're hoping to do is find a middle ground by treating this as a natural logic inference task. Okay, so this has been work that's been done by my PhD student, Gabor Anjali, in the last couple of years. So we start off with this large pile of text, which we're going to treat as our knowledge base. And then you might think that what we could do was infer new facts from that. And in principle we could, but you know, we have an enormous amount of text and it's probably inconsistent in all sorts of ways. And so we wouldn't really want to try and run inferences over combining all of these facts and seeing what we could derive from them. So instead what we're going to do is the opposite, that we're going to infer whether things are facts on demand from a query. So if we have a query of interest, we think it might be the case that no carnivores eat animals, then what we want to be able to do is run backwards from that query to see what our knowledge base says. And so we're going to do steps here, which are then steps of natural language inference. So from no carnivores eat animals, we can tell that that would be contradicted by the carnivores eat animals, and that this fact would be consistent with a cat eats animals, and that would be consistent with a cat eating an animal, which would be consistent with a cat eating a mouse. And so therefore, if we've got a fact of a cat eating a mouse, that would contradict that no carnivores eat animals. And so that's the kind of style of natural logic inference that we want to do. Of course, we can't expect to get lucky the first time we start expanding things. So really we're going to explore down in a large search, and as we explore down the search, we're going to try and find stuff that matches in our knowledge base. And so the central natural logic inference question is, if I mutate a sentence in some way, do I preserve its truth? So we want to know that if all young rabbits drink milk, can we therefore say all rabbits drink milk? And the answer is no, that's not a valid conclusion. But if some young rabbits drink milk, then we do know that some rabbits drink milk. That is a valid conclusion. And so we want to build a calculus that allows us to do these kind of natural logic inferences. And one of the concerns of that is that we need to understand polarity. So one source of inference we have is set containment relationships between words. So we know that a cat is a kind of feline, is a kind of animal, and that will allow us to make certain inferences. So if we know that some cats drink milk, we know that some animals drink milk. But that when we can make these kind of inferences is affected by whether you're in a positive or a negative context. So we also need to know the polarity, the direction a phrase can move in this ordering. So if it's the context that I just said of some cats drink milk, therefore some animals drink milk, we can be sort of moving upwards. But in a negative context, we'd be moving downwards. And what we find is that different linguistic operators, like quantifiers, respect different polarities. So if we start off with a sentence like all cats eat mice, then the valid inferences in this first noun phrase position are going downward in specificity. So if all cats eat mice, then all house cats eat mice. This position goes up. If all house cats eat mice, then all house cats consume mice, but it does not mean that they slurp mice. And in the final position over here, again, you're allowed to go upwards. So going downwards is invalid, but going upwards is valid. So we had this result that you could infer downward in this position and upward in these two positions and get valid inferences. And so that's understanding the polarity of different positions as to when you could infer upward or downward. Okay, so what's good about using a natural logic proof method like this? A great thing about it is it's actually very computationally fast during inference, so that we don't have a semantics as some kind of logical knowledge representation that's hard to get at with a lot of uncertainty, that all we're using is a straightforward syntactic parse, and our steps of logical inference are just changing a word, adding or deleting a word. It's computationally fast to pre-process. We're just using plain text. And it's a weak logic. It doesn't allow all of the theorem-proving results of, say, first-order predicate calculus, but actually captures most of the common types of inferences that come up all the time and which human readers can be expected to make instantly. Okay, and so that's essentially what we're doing. So we have this big text space, and we'd like to decide which things are invalid or not, and we're starting with what we'd like to improve and doing this search. And so as we search, we're having these steps that we go through. So start with no carnivores eat animals. We consider one-word mutations of that, changing words or adding or deleting. And then we're working out their logical relationship. So this one is these two contradict each other. Then the logical relationship of these two is this one supports this one. And we head on down until eventually we find a fact that we have a piece of text in our knowledge base, and then we can decide what the truth status of our starting out statement or question is. So we've applied this idea to a couple of example problems of common sense reasoning and question answering, and so I'll finish by just telling you a bit about these. So one first set of experiments was with common sense reasoning facts. And so a group at MIT have developed ConceptNet, which was meant to be a sort of a database of common sense facts in a formalized representation, like not all birds can fly, noses are used to smell, music is used for pleasure. And so we thought we could just see whether, starting with the plain text that we had gotten off the internet, whether we could successfully infer those things. So we got a second data set, which was then taken from a previous system from the University of Washington. They've worked a lot on open information extraction, of trying to get facts out of web pages. And so we took a collection of extracted facts from their system. We manually filtered it for correctness, and that got a balanced data set, which is pretty easy because the accuracy of their facts is at best 50%. And so for our source knowledge base, in this case, we start with clauses which actually come from a different University of Washington open information extraction system. So we get as our starting point these clauses like Obama was born in Hawaii. And I'll say in a minute how we have a method now for cutting up whole sentences into these shorter clauses ourselves. But here are some results from this system. So one thing we could do is just do direct lookup. So if we're being asked not all birds can fly, true or false, we could just look at our big pile of text and see whether the fact is in that pile of text. And if so, it turns out we get everything right, which reflects the fact that at least for these examples, the correct answer is at least always more frequent than any wrong answers. But our recall is very low. But then we can start using naturally to try and infer answers using natural logic inference steps. And if we do that, our precision goes down a little bit, but our recall goes up enormously, that we're able to quadruple the number of times that we're able to work out the right answer. And so that's really nice. And in particular, if you don't allow answers the direct lookup, naturally can really do almost as well by having to infer an answer. Okay, so that was a starting proof of system, but there was one bit I kind of skipped over, which was I sort of said that our knowledge base was just a big pile of text, but actually the knowledge base for that example, we're using individual simple subject, verb, object style predicates like the cat ate a mouse, which we'd actually gotten from the UW information extraction system, OLI. So what we'd like to do is fully be able to have a knowledge base that starts off with these just complex, nasty, real-world sentences. And so we also did some work for that. And the interesting thing is you can also actually think of this as a problem in natural logic. So what we'd like to do is start off with big, long, real sentences and then get out of it shorter, simple sentences. And the ones that we'd like to get out are the ones that can be supported as natural logic inferences. Okay, so how do we do that? Well, for the syntactic representation that we've been using, this has been using a representation called universal dependencies, which builds on earlier work that we did at Stanford on Stanford dependencies. And so the idea of Stanford dependencies was to give a single level of type dependency syntax that gives a simple human-friendly representation of sentence structure and meaning. Dependency representations of linguistic structure have actually been exceedingly popular and a lot of the development of them has happened in places like Russia, so I hope some of you have seen these representations before. And so these have turned out to be very friendly representations for machine interpretation because they're almost a semantic network. And so the idea of universal dependencies is to be a version 2 of this that's linguistically better across languages than earlier representations. And so this is a project that a whole bunch of us are working on, and you can find it on the web at this address. Happy to have other people involved in that. So in the context here, what we're going to do is we're going to start with real sentences with their universal dependency syntactic parse done automatically, and we have actually a neural network dependency parser that works very well for that. And then what we're going to want to do is split it up into clauses. And the main trick for that, which we build a simple classifier for, is when we split clauses, we need to add their shared arguments. So when it's born in Hawaii, Obama is a US citizen, we want to not just get out born in Hawaii, but Obama was born in Hawaii. And so we have a supervised learning system which tries to yield entailed clauses. So it goes breadth first down the search tree, and at each point it decides is it a point where it can extract a clause. It could extract a clause providing it fills in the subject of the current clause from a higher argument of a higher clause, or whether it should continue searching downwards, or whether it's gotten below the level of the smallest clause and it should stop. And we're able to train this using the idea of distance supervised training, where we haven't actually labeled sentences for this, but we've just trained it based on things that we know about as good extractions in the past using the OLI data that we classified previously. And so the object, again, is to use the natural logic idea that we can shorten clauses in any way that preserves validity. So from all young rabbits drink milk, we don't want to shorten it to all rabbits drink milk, but from some young rabbits drink milk, we can shorten it to some rabbits drink milk. So in that way, we use natural logic to get these short little snippets of language which is still valid. And so that's sort of the same idea as before, that we're manipulating around modifications and seeing what we can do. As a result of that, we've effectively built our own open information extraction system, where we take sentences of whole sentences from the web, we divide them into clauses using our classifier, and then we shorten them using natural logic. And I'm going to finish by presenting two of the things that we've done with that. One is just to use it as an open information extraction system and see how well it works. And then the other is actually to do a question answering task, which immediately actually relates into the task that the hackathon is looking at. So for evaluating it for filling a knowledge base, we compared our results on the US NIST TAC knowledge base population task. So this is a task where you're wanting to get out facts such as somebody is somebody's spouse or somebody works for some company. And most of the systems that do that build large supervised relation extractors, training carefully on labeled data or databases of correct extractions. And we've built that kind of system as well, actually. But what we wanted to compare is that the University of Washington had also entered their open information extraction systems into this competition, and we hoped that by having the greatest semantic precision of natural logic that we could do somewhat better. And indeed we were able to. So the University of Washington system was able to get an F1 measure of about 19.6, which we were able to replicate doing it ourselves, which is always pleasing. And our naturally system was actually able to do somewhat better than that. And in particular, the right comparison is between these two systems, because the actual UW submission used an earlier open information extraction system, and then also used some handwritten hacks to improve their precision, where the true comparison is sort of between Oli's precision and recall, and use of natural logic is actually kind of giving a noticeable bump in both of those. Of course, UW isn't the only person who can put in some hacks to improve precision and recall. We were able to add some bells and whistles onto our system and further improve its recall. Some of the getting better recall is things like being able to recognize names that are the same names, like Bob and Robert are likely to be the same. And so we're able to sort of actually produce a pure natural logic system that actually is doing pretty decently in the TAC KBP competition, better than the median entry in that competition, though still well below the best systems, which include our own best system. Okay, so that's OpenIE as natural logic, because really you can think of OpenIE as a sentence simplification task, and sentence simplification you can think of as doing natural logic. I guess I haven't updated this. This actually has now been released in Stanford Core NLP. So the most recent 3.6 release of our NLP, open source NLP software, you can now ask for natural logic, positive negativity annotation, and open information extraction, and you'll actually then be able to get open information extraction triples coming off of sentences. Okay, so to learn natural language inference on real English, we need to teach a model English almost from scratch. And previously, there hasn't been a ton of data available for doing that. And so I just thought I'd mention one other new resource that we've built recently, is the Stanford Natural Language Inference Corpus, which is a very large supply of examples where we got Turkers to write sentences where they're pretending they were describing a photo and then making sentences that were either contradictory or consistent or inferable from another sentence. And so that's actually quite a nice new resource for testing models for natural language inference. Okay, so that's the end of what I was going to say. So that, the theme was how much effort should we do into making use of linguistic and knowledge representations for our inference. That some people have been trying to go extremely minimalist with, no knowledge representations. All we have for language is sequences. Sometimes then it starts to get a bit more complexified with memory and attention. I kind of feel that we want a little bit more than that, and that there is surely a right middle ground of simple representations that get at the central heart of language while not being overly complex. And I think the key to that is realizing that language and many other things does have this compositional structure where parts go together to build bigger parts, and so you get these kind of tree-structured models. And so I've been enthusiastic in the work that's been done on tree-structured or equivalently stacked neural networks. As you probably remember from some formal languages class, as soon as you have a stack, that gives you the equivalent power of trees. Lots of other good ideas, universal dependencies, natural logic, inference, and going together that I think can be powerful ideas for leading to better natural language understanding and question answering systems. And indeed, in very recent work, we've actually been taking some of the ideas of that natural logic inference system and ourselves been applying it to some of the science question answering data of the same kind that of the Allen AI Institute that you've been looking at in the hackathon. Okay, thank you.
Thank you, Chris. Yes, now do you have time for questions?
Sure.
Okay. Who want to ask a question?
Yes, I'm curious. You are talking a lot about logic, but you did not mention.
Sorry, Chris, turn off your when we are asking you because we have echo. Okay, now it's much better.
Also, you talk a lot about logical inference, but you did not mention rhetorical structure theory. But I think, let's say, in the context of sentence simplification, it is quite natural to see if you see a clause, another clause, and what is the relation between this clause, right? So, do you think it is relevant in these problems? Thank you.
Good question. That's not something I've worked on myself a lot. So I think, in principle, yes, absolutely, and it's definitely something we should be doing. In practice, I think one of the problems has been that the ability to correctly decide discourse relations like rhetorical structure theory relations is very modest. I mean, I think maybe that's something where, you know, even if you get human beings to do it, it's very hard to get agreement. So even though it's clearly true there are relations between clauses, perhaps, you know, the set of rhetorical structure theory relations, that they overlap in many ways, and it's not actually necessarily a good classification task. But the fact that you want to understand relationships between clauses, I think, actually is something that's very important. And I mean, a place that's actually been coming up for us is recently we've been looking at the data set from the Google DeepMind people of looking at Daily Mail and CNN question answering, and some of our impressions of that is that, well, there's a large percentage of the questions that you can answer just from a single clause or sentence, and then you don't need anything more than that. But for the ones, is that still good? You still good? Yeah. For the ones where it does extend across sentences, it seems a key of a lot of what you need is actually to have discourse relationships between the two clauses. So I think it is important.
Okay, thank you. Next question. Yes.
Thank you for the great lecture. I want to. What? Can you hear me? Oh yeah. So I wanted to ask, is there maybe an field or maybe some theories about creating some base, like minimal knowledge base with, I mean, like some weights that are maximum, and then trying to expand with some frameworks like OpenIE or some else like Carnegie Mellon's NEL or some other automatic knowledge-based constructor, but have some core of beliefs that are central and presumed to be more correct than others. So to have some measure of plausibility of some facts or any other constructions in language.
There's there certainly have been ideas along those lines. I mean, someone who's argued for a position like that would be Bruce Porter from the University of Texas, and he strongly believes that there are these sort of central core theories that should be hand specified, and then you could build out from there. I mean, I think in practice, for the kind of empirical work that's been done so far with common sense reasoning and question answering, to me it's never been clear that these sort of of this, and I mean, in some sense you could say that what you get for the Google Knowledge Graph is a version of that, in which they have the core knowledge, which is hand-built originally, most of it from Freebase, as you know, and then they've attempted to expand that out with further knowledge that's mined from data, and certainly then they're trying to sort of filter it as to how true they believe it to be. So I think trying to do that kind of automatic knowledge expansion and then filtering it for sort of belief consistency based on existing facts is certainly a good research direction. I think until now it's actually been kind of hard to do. I mean, we've actually tried to do a version of this inside our knowledge-based population work, because in that work also you start with an initial knowledge base and you try and expand it by reading. So that might be interesting to look at some of the papers doing that. And although in some simple cases we can use the existing knowledge base to filter which extractions from text we take, in general we've sort of found it hard to get very large gains by trying to do that kind of inferencing.
Okay, thank you. More questions? Yes.
Hey, thank you for election. So I want to touch such question. You argued themes that we have data of a priori known nature language. Yes, that is. So, and what do you think about the mission of SETI, yes, of searching of extraterrestrial intelligence signals, yes, and what can be done in analysis of such a kind of signals? I mean, when we have a signal, yes, which received from OpenSpace, yes, it consists of some few non-random structures, yes, possibly intelligent structures that could be analyzed for future understanding, yes, such as a problem of Fermi paradox, yes, we have a Drake equation on the other side, we have some complexity, Kolmogorov complexity, such kind of methods. So what do you think about these trends in SETI, yes, in Fermi paradox, and in analyzing of non-random structures? Thank you.
I'm afraid I think that's a topic that I'm not very expert in. I think there's, certainly a starting point that we can use ideas of information theory and expect that we should be able to see structures in signals that are used for communication that don't exist in just random signals like random noise, but that's not something I've ever really thought about much, so I'm not sure I have anything very wise to say about that.
Thank you.
Thank you. It's like, can we classify white noise for different, like doing topical classification of white noise? What we will have from this, or from some noise from space? Yes.
Right, but it's certainly not supervised classification because, well, it's certainly not easy supervised classification because it seems like there's not one kind of signal that could be communicative. It's a big disjunction over different ways that you could think of encoding information in signals.
Okay, thank you. So, more questions? No. Oh, last question.
Actually, it's not a question. I just wanted to help to thank you for your Coursera in 2012, as I remember. It was very great. Thank you.
Thank you. I'm glad you enjoyed it, and thank you to everyone for being at the talk today, and my apologies for being so late getting started.
Okay.
Okay, thank Chris.